Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is part winding reduced voltage starters. Our objective is to introduce the part winding reduced voltage starting method. Reduced voltage starting methods reduce inrush current and modify acceleration and starting torque characteristics. This lecture operates under the assumption you've watched the primary resistors, reduced voltage starters, and motor connection diagrams lectures, both available at the Big Bad Tech channel. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time to do so now. As you are no doubt sick of me reminding you, the direct and instantaneous application of full voltage to a motor at standstill produces a tremendous surge of current known as inrush. Although brief, inrush can place an unnecessarily high demand on the electrical distribution network, and industries often pay a financial penalty for such events. Additionally, the abrupt acceleration of a motor at standstill may damage the mechanical linkages, like belts, chains, shafts, gears, and couplings the system uses to manipulate the applied load. It is for this reason reduced voltage starting methods are employed. Reduced voltage starting methods include, but are not limited to, primary resistors, part winding, Y-start delta run, sometimes called a star-delta starter, soft starters, and motor drives. All these methods serve to limit inrush current and limit mechanical stresses to the driven load. Today we'll discuss one of these methods, part winding reduced voltage starters, on an introductory level. After we've discussed timer relays, expect to revisit reduced voltage starters incorporating timers in later lectures. As the title implies, part winding reduced voltage starters use only a portion of the available stator windings when starting a motor. As you'll soon learn, reduced voltage should be in quotes because it's actually a bit of a misnomer. However, the effects are the same. A motor when started in part winding mode experiences less of an inrush and accelerates gently in comparison to a full voltage starter. Part winding reduced voltage starters can only be used for low voltage configurations of dual voltage motors. As you'll recall from the motor connection diagrams lecture, this rules out all 3-lead and 6-lead motors, and all high voltage configurations of 9-lead and 12-lead motors, leaving us 9-lead pre-configured Ys in low voltage configurations, 9-lead pre-configured deltas in low voltage configurations, 12 leads configured as Ys in low voltage configurations, and 12-lead motors configured as deltas in low voltage configurations eligible for this technique. The commonality exhibited by these motors is that they are all dual voltage motors in the low voltage configuration. Dual voltage motors ordinarily have 2 windings per phase. Low voltage configurations ordinarily wire these 2 windings in parallel with one another. Consider a 9 or 12 lead motor in the low voltage Y configuration. Skipping over the gory details of the connection diagrams, ultimately winding A1 is in parallel with winding A2, and similarly, B1 is in parallel with B2, and C1 is in parallel with C2. Each phase of a full voltage motor starter therefore sees the parallel combination of 2 windings. Parallel combinations, if you'll recall, always reduce resistance seen between 2 terminals because a voltage source sees 2 available paths for current. A part winding reduced voltage starter separates the parallel windings. One set of windings only is used to start the motor, and then, after the motor accelerates to an acceptable speed, both sets in parallel are used to run the motor. In start mode, only the start or S contactor closes, and only windings A1, B1, and C1 form a Y configuration. The Y formed by windings A2, B2, and C2 is disconnected and does not allow primary current flow. Each phase therefore sees only one available path for current, and as a result, inrush current is reduced because resistance has increased. As I mentioned earlier, the term reduced voltage is a bit of a misnomer, since the Y formed by the windings A1, B1, and C1 still experiences full voltage in start mode. However, the effects are the same. Inrush current and mechanical stresses to the applied load are reduced in start mode. At a certain point, the motor is accelerated to an acceptable speed, and the second set of windings is connected in parallel. In run mode, both the start, or S contactor, and run, or R contactor, are closed. Full voltage is applied to both sets of windings in parallel to a motor already rotating close to nominal speed. Given the motor is not at a standstill, inrush current occurs. However, it is again substantially less than if the motor was in locked rotor conditions. Note the part winding reduced voltage starter method utilizes two contactors, start and run, and two overloads, OLS and OLR. Primary current in run mode is essentially divided between two paths. The contactors and overloads must be rated and set for the set of windings they serve. Finally, note that the start and run winding sets must be connected such that they produce the same rotational direction of the rotating magnetic field. Failure to follow the motor connection diagram judiciously could result in a configuration in which the start and run winding sets produce equal yet opposite rotating magnetic fields. This is bad and to be avoided at all costs. Part winding reduced voltage starters needn't be limited to Y configurations. Consider a 9 or 12 lead motor configured as a low voltage delta. Low voltage configurations ordinarily place the windings in parallel with one another, such that winding A1 is in parallel with A2, and similarly, B1 and B2, C1 and C2. A part winding reduced voltage starter would make use of only one set of windings for start mode and both sets of windings in parallel for run mode. The graph of inrush current for the part winding reduced voltage starter method shows characteristics common of a closed transition reduced voltage starter. As you recall from our preliminary discussion on this topic from the primary resistors reduced voltage starters lecture, a closed transition reduced voltage starter never de-energizes the motor during a transition from start to run, even momentarily. There's always a pair of hands under it, ushering it along, and there's not a jarring disjoint in the transition. This isn't always the case for other reduced voltage starter methods. Consider an open transition reduced voltage starter that must necessarily de-energize a spinning motor, even momentarily, during the transition from start to run. This would be a graph characteristic of an open transition reduced voltage starter. Notice the transient spike that occurs during the open shift that does not occur in the closed transition reduced voltage starter. The spike is a product of the open transition. Open transition starters try to minimize the transition time to minimize the disturbance. However, it's an intrinsic characteristic of open transition methods. We'll revisit open transition reduced voltage starters in later lectures. Note the part winding reduced voltage starter method never de-energizes the original start Y configuration. Therefore, it wouldn't be expected to exhibit a transient spike. As long as we're looking at these graphs, we should discuss how the timing of the transition from part winding to all windings in parallel affects the inrush current. Note if the transition from start to run takes place quickly, the motor is only given a short time to accelerate. Inrush current in the closed transition will be more. If the transition from start to run mode takes place later, the motor is given more time to accelerate. Inrush current during the closed transition will therefore be less. Thus far, we've examined only the primary schematic of the part winding reduced voltage starter method. Let's take a look at some sample pilot schematics that govern their operation. These configurations will be very similar to the pilot schematics we previously discussed in the primary resistor reduced voltage starter method lecture. Our first ladder logic example of a part winding reduced voltage starter features an operator-initiated start, followed by an operator-initiated transition from start to run. Rung 1 and 2 consist of a 3-wire control circuit governing the start contactor only. Rung 3 and 4 consist of a 3-wire control circuit governing the run contactor only. Note the normally open S2 contact in rung 3. This prevents an operator from closing the run contactor only without having first closed the start contactor. Note the overload contacts, OLS and OLR, are in series with one another. An overload in either set of windings would de-energize the motor. When an operator presses and releases the start button, the S contactor coil is energized and its associated contacts change states. The S primary contacts close, and only one of the Y configurations is connected to primary voltage. Given there is only one path for current, the part winding starter limits inrush current. The S1 holding contact closes, as does the S2 electrical interlock in rung 3. An operator witnessing the motor and applied load come up to rated speed then initiates a transition to run mode by pressing and releasing the run button. The R primary contacts close, and a second set of windings are connected in parallel. Full voltage is applied to both sets of motor windings. The R1 holding contact closes. Note the E-stop, stop, and normally closed overload contacts serve to de-energize both the start and run contactor coils, thus opening both primary contacts and de-energizing the motor. The fundamental flaw to our system as currently implemented is that it relies upon the judgment of an operator to initiate the transition from start to run. Operators, like most of humanity, have a reputation of being fickle mushheads and cannot normally be relied upon to make consistent and sound judgments based off only visual and audible clues. It is for this reason the manual run button has been replaced in our second iteration with a rotational speed switch that closes when the motor has reached an acceptable transition speed. Note that since the operator's subjective judgment has been removed, it's really not necessary to include the S2 electrical interlock as previously. The operator still initiates a start by pressing and releasing the start push button. However, only when the motor has reached the set speed of the rotational speed switch does the system automatically initiate a transition from start to run mode. Note holding contact R1 keeps both sets of windings connected to full voltage in the event of a momentary drop in speed. The setting of the rotational speed switch can be reduced such that the transition occurs early, or the setting of the rotational speed switch could be increased such that the transition occurs later, depending upon the needs of the mechanical system and the desire to limit disturbances on the electrical distribution network. Note the transition between start, partial winding mode, and run, all windings mode, could also be time-based rather than speed-based. We'll discuss reduced voltage starters using timers in later lectures. Here's a graph of line current for a regular full voltage starter for a lightly loaded 9-lead Y-configured motor in the low voltage configuration with both sets of windings in parallel. The vertical scale is set to 5 amps per division, and the horizontal scale is set to 1 second per division. Notice the huge current draw, peaking out around 12-ish amps upon being instantaneously and directly connected to full voltage. Additionally, note the motor accelerates briskly and reaches a stable current draw in less than 1 division, meaning it took the motor less than a second to accelerate the applied load. This would be the method of choice for a fragile electrical distribution network or applied loads necessitating controlled acceleration. In contrast, consider the graph of line current for a part winding reduced voltage starter used on the same lightly loaded 9-lead Y-configured motor, when only one set of windings is energized by full voltage. The vertical and horizontal scales are set to the same respective 5 amps per division and 1 second per division. Notice the motor now takes 6 to 6 1/4 divisions, or just over 6 seconds to accelerate the applied load. Additionally, note that current draw peaks out at only 6 amps. The part winding reduced voltage starter therefore serves to limit inrush current demand and mechanical stresses to the applied load. Note, due to the lengthy acceleration period and comparatively small current draw, part winding reduced voltage starters may have difficulty breaking the static inertia of a large applied load. Note, part winding starters sometimes sound awful during the acceleration period. Here's both curves superimposed on one another so you can compare the two methods. The full voltage starter is in blue. It is characterized by substantial inrush and a brief acceleration period. The part winding reduced voltage starter is in yellow. It is characterized by substantially less inrush and substantially longer acceleration. Alright, this about wraps up our introduction to part winding reduced voltage starters. In conclusion, this lecture took a brief look at part winding reduced voltage starters. We learned reduced voltage starters are used to reduce inrush current and modify acceleration and starting torque characteristics. Only dual voltage motors in the low voltage configuration can make use of this technique, thereby limiting its applicability to these devices. When started, only one set of windings is connected to full voltage, and once the motor reaches a predetermined speed, or after a predetermined period of acceleration, the other set of windings is connected in parallel. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.